Welcome to this explainer. Okay, if you've ever stared at a page packed with X's and Y's and felt like you were trying to decode some kind of alien language, hey, you're absolutely not alone. It can feel like a totally frustrating jumble of letters and numbers. But today, we're going to completely reframe algebra. We're going to transform it into exactly what it was always meant to be, a highly logical, massive time-saving toolkit. By the end of this explainer, you're going to see that algebra isn't just a bunch of arbitrary, stuffy rules made up by math teachers. It's actually the underlying blueprint of reality.
Right off the bat, let's look at a super simple puzzle. What goes in the empty box here? Box times 3 equals 15. Now, your brain probably jumped immediately to the number 5, right? Because, well, 5 times 3 is 15. Well, congratulations. That right there proves that through basic childhood counting, you actually already know how to do algebra. Literally, the only difference is we usually replace that little box with a letter, like X. That's the whole secret. A variable is just an empty box waiting for a number. So, to build out your mathematical utility belt piece by piece, here's our roadmap for this explainer. We'll be hitting the blueprint of algebra, decoding algebraic identities, the quadratic puzzle, predicting patterns and sequences, and finally wrapping up with the advanced math toolkit. All right, let's jump straight into section 1, the blueprint of algebra. Now, the first thing we need to do is clearly contrast our two main playing pieces. On one side, we have an expression. Think of this as a simple mathematical phrase. It has terms, maybe a few constants and variables, but no equal sign. It just kind of is what it is. On the other side, though, we have an equation. And an equation is a fully balanced scale. It takes two expressions and firmly declares that they weigh the exact same amount. That equal sign, it's the fulcrum of our whole scale. And that brings us to the absolutely crucial concept of balance, which leads right into the golden rule of equations. If that equal sign is a perfectly balanced scale, then whatever changes you make to one side literally must be mirrored exactly on the other. Add 5 to the left, you gotta add 5 to the right. Divide the left by x, you divide the right by x. It is the ultimate rule of mathematical fairness. You just can't cheat the scale. To actually manipulate our equations without breaking that perfect balance, we rely on 3 unbreakable laws. First up, the commutative rule. This just tells us the order of addition or multiplication doesn't matter. A plus B is exactly the same as B plus A. Simple enough. Second, the associative rule says how we group terms when adding or multiplying doesn't change the outcome. And third, the distributive rule. This one allows us to multiply a number across a sum inside parentheses. Basically, multiplying a number by a sum gives you the exact same result as the sum of their individual products. These 3 rules dictate exactly how we can shuffle our numbers and variables around. Moving right along, let's hit section 2, decoding algebraic identities. Now, you've likely seen the formula for a minus b whole squared before. And honestly, maybe you just memorized it for a test. But instead of blindly memorizing it, this step-by-step expansion proves that formulas aren't magic. They're just pure logic playing out. By simply multiplying the terms out using our trusty distributive rule and combining the like terms in the middle, we arrive at a squared minus 2ab plus b squared. It's just a proven shortcut. Okay, but why does this matter? Why do we actually care about these algebraic shortcuts in the real world? Well, let's do a quick mental test. How fast can you figure out this complex arithmetic problem? 297 times 303. In your head, totally without a calculator. It seems super daunting, right? Got it yet? The answer is 89,991. I know, it sounds wild to do that in your head, but believe it or not, it only takes seconds to solve when you pull the right gadget out of your new utility belt. Let me show you exactly how this works. This is where the magic happens, brilliantly illustrating the power of algebraic identities. We can rewrite 297 as 300 minus 3, right? And 303 is just 300 plus 3. This perfectly matches our difference of squares algebraic formula. A minus b times a plus b equals a squared minus b squared. Suddenly, instead of terrible, messy multiplication, you're just doing 300 squared, which is an easy 90,000, minus 3 squared, which is 9. 90,000 minus 9 is 89,991. Boom. We just use letters to turn a tedious calculation into a massive mental time saver. Let's level up a bit. Section 3, the quadratic puzzle. Up until now, we've dealt with pretty simple unknown variables. But when our puzzles involve a variable that is squared, an x squared, they take this general form right here. Ax squared plus bx plus c equals 0. Because of that squared term, simple balancing just isn't going to cut it anymore. We require some heavy-duty machinery. the famous quadratic formula to quickly find those unknown values of x. But here's my absolute favorite part. Nestled inside that quadratic formula is a fascinating little piece of math called the determinant, or the discriminant. It's b squared minus 4ac. What's amazing here is that this discriminant acts exactly like a secret decoder ring. Before you even fully solve the puzzle, just looking at this one tiny calculation instantly predicts the types of answers you're going to find. Greater than 0, you're looking for two distinct real numbers. Exactly 0? There's just one repeating real answer. Less than 0? Well, buckle up because you're stepping into the wild, weird world of imaginary roots.
Moving on to Section 4, predicting patterns and sequences. Now we're scaling up from finding a single hidden number to basically predicting mathematical futures. This neatly contrasts our two main types of sequences. First, the arithmetic sequence, where you just add a constant value to get the next number, kind of like counting by threes. And then the geometric sequence, where you multiply by a constant, like, say, doubling your money every day. By using these specific algebraic formulas, we completely bypass tedious counting. If you want to know the thousandth term of a sequence, you don't have to count it out. Just plug 1,000 in for n and let the algebra do all the heavy lifting instantly. Okay, and this builds to an absolutely incredible concept. What if a sequence goes on forever? Can you literally add up an infinite number of things and actually get a normal, finite number? Mind-bending, but yes, you totally can. This beautifully simple formula allows us to calculate the exact sum of an infinite sequence of geometric terms, provided that the multiplier r shrinks the values fast enough. It is literally infinity, tamed by a tiny piece of algebra. Just incredible. Finally, let's bring it all home with Section 5, the Advanced Math Toolkit. Each of these specialized tools takes our algebraic logic and expands it into entirely new dimensions. Logarithms allow us to take unimaginably massive exponential growth and simplify it way down to basic addition and multiplication. Permutations and combinations give us the power to instantly calculate thousands of different potential groupings and arrangements without ever having to list them all out manually. And vector algebra takes our numbers completely off the flat page. It gives them magnitude and direction, allowing us to mathematically map and navigate entire 3D spaces. And we absolutely can't forget the digital world. Taking this logical framework into computing, we have Boolean algebra. This is an entirely different flavor of algebra that works strictly with binary variables, just ones and zeros, true or false. Using core laws like identity, null, and double negation, Boolean algebra forms the exact mathematical foundation of modern computer science, software programming, and electronic circuit design. Literally, the screen you are watching this explainer on right now, it is running on Boolean algebra. So from balancing a simple scale with an equals sign to mapping 3D space and even powering global computer networks, algebra truly is the hidden language of the universe. It's definitely not some frustrating set of hurdles. It's a remarkably powerful real-world utility belt. Now that you understand how this logical toolkit really functions, the only question left is, what real-world puzzle will you use it to conquer next? Thanks for hanging out and learning with me today, and keep exploring.